share the screen. We're going to start our class for Physics 103. Faraday's law of electromagnetic induction. Introduction. On magnetic fields we study under electrostatics and electrodynamics are produced by stationary and moving charges, respectively. When electric field is applied to a conductor, current is produced, which in turn generates a magnetic field. One could rightly ask whether or not an electric field could be produced by a magnetic field. Faraday's experiment explained this. Michael Faraday's discovery of 1831 shows clearly that by changing magnetic fields with time, electric fields could be produced. The phenomena is known as electromagnetic induction. The figure on the next slides tells us. You can see 3 pallets. In the first pallet, this is a galvanometer, this is a coil of wire, and when a magnet is brought close to the wire loop, there is a rightward deflection, which shows that current flows in the positive direction. Here the magnet is held stationary and there is no deflection. In the third pallet, the galvanometer, the magnet is moved away from the wire loop and you see a deflection but in the opposite direction. Faraday's experiment shows that no current is registered in the galvanometer when the bar magnet is held stationary with respect to the loop. However, a current is induced in the loop when relative motion exists between the bar magnet and the loop. Faraday's experiment demonstrates that electric current is induced in the loop by changing the magnetic field. Let us look at magnetic flux. Let's consider a surface with the area vector A and the magnetic field B, making an angle theta with the area vector. Let the area vector be A equals to magnitude of A and the unit normal n. The magnetic field flux through the surface is given by phi B equals to magnetic field dot A, and that gives us effectively the magnitude of B, the magnitude of A, and the cosine of the angle theta. Theta is the angle between B and the unit normal n. If the field is non-uniform, phi B then becomes the surface integral B dA. The SI unit of magnetic flux is Weber. 1 Weber is expressed as 1 Tesla times meter squared. Faraday's law of induction may be stated as follows. The induced EMF in a coil is proportional to the negative of the rate of change of magnetic flux. And mathematically, this is the equation. If we have a coil consisting of n loops, the total induced EMF would then be n times as large. This is equation 4. Now, let's see how we got this. We said can you see that? We said for a uniform field, the magnetic flux is given by Faraday is equals to the magnitude of B, magnitude of A, and the cosine of theta. We also said the EMF is giving us the what? The negative of the rate of change of the magnetic flux. Now, EMF would then be equals to, let's use square braces, d by dt b a cos theta. This gives us what? Look at this. We have three functions in the bracket b, a, and cos theta. And accordingly, the differentiation will yield what? Minus a cos theta dB dt minus b cos theta dA dt plus BA sin theta d theta dt. This is the equation we have here. And it implies that the EMF could be obtained in any of the following ways. First of all, we could obtain the EMF by varying the magnitude of B with time. You can see in the first palette, the magnetic field strength is high within the coil. In this case, we have reduced the strength of the field. So the field in the first palette is greater than the field in the second palette. That's the first term of the equation. But we can also induce EMF by varying the magnitude of A, the area enclosed by the loop with time. Can you see this? The third way to induce EMF is by varying the angle between B and the area vector A with time, as you can see. In the next class, we look at Lenz's law, because we're interested in knowing the direction of the induced current. Lenz's law answers this crucial question Lenz's law is the following statement. The induced current produces magnetic fields which tend to oppose the change in magnetic flux that induces such currents.